Hey there everyone, and welcome to the second video in the subunit on complex functions. In this video we'll talk about limits and continuity. The reason we need to talk about these things is that we're trying to define eventually the derivative of a complex function, and just like in Calculus 1, a derivative is a limit, which is why we need to talk about limits, and all differentiable complex functions are continuous, so we'll also briefly talk about continuity. So, two things in this video. What does it mean to take a limit of a complex function? And what would it mean for a complex function to be continuous? Those are the two things to cover for now. So just recall what you all hopefully remember from Calculus 1 or maybe Calculus 3, something like that. But with real numbers, and in particular with a single variable real function, we all know what a limit means, I think. So something like this statement. Limit as x approaches 4 of f of x equals L in plain English means if you let the inputs get really close to 4, then the outputs, so the values of f, will get really close to L. So if this were a 7 or something, you'd be saying if we make x really close to 4, then f of x will get really close to 7. That's the friendly definition of limit that you saw in Calculus 1 several times. So if you want to think about, well, what corresponding statement would you make with the complex numbers? Surely you would just say something like this. As complex number z, input z gets really close to a plus bi, what does f of z do? Well, if it gets really close to c plus di, then we can make this statement, that as z approaches a plus bi, the limit of f of z is c plus di. So it's the exact same definition as in the real numbers, but just now we have complexes floating around. So this is what it means to take a complex limit. So here's an example. As z gets close to 4 minus 2i, we can ask, what does z squared do? And it turns out that z squared gets really close, arbitrarily close to 12 minus 16i. If we let z get really close to 4 minus 2i, the outputs will approach 12 minus 16i. The one wrinkle now, though, in contrast to the Calc 1 setting, letting x get really close to 4 in a single variable setting, you're just on the x-axis. So you can approach 4 from the left or the right, but there's no other way to approach 4. In a situation like this, where 4 minus 2i is sitting in the complex plane, you can walk towards 4 minus 2i from a bunch of different directions. You can come in from the north, come in from the south, from the west. You can come in from the the northwest. You can spiral your way into 4 minus 2i. There are many ways you can walk towards 4 minus 2i. And what this limit statement is asserting is that, well, no matter how you walk towards 4 minus 2i, the outputs will get close to 12 minus 16i, which notice is the same thing as 4 minus 2i quantity squared. And you can convince yourself of this in a number of ways, but probably the easiest thing to do would just be take complex numbers really close to 4 minus 2i and square them and just see where those outputs are going. It's pretty clear they're going to go towards 12 minus 16i. I'm not proving that to you formally. I'm just saying you could convince yourself of that with some playing around. But the point I want to make here is there are many ways you can walk towards 4 minus 2i. No matter how you approach 4 minus 2i, the outputs need to approach 12 minus 16i to make this limit equation true. And I don't expect you to have this at your fingertips, but hopefully something in your Calc 3 brain is tingling right now or something. This should look very familiar to you, to the kinds of limits that we dealt with in Calc 3, where we would let, let's say, x comma y approach 4 comma negative 2. And we'd be sitting in the xy plane. Approaching the point 4 negative 2 instead of approaching the number 4 minus 2i, but it's the same kind of flavor. Okay, so how could a limit fail to exist? Here's an example like that. So here's a piecewise function. This is just saying that for any complex number, if the distance from that number to the origin is less than 1, then when we input that complex number into this function, it will output an I. If, though, your complex number is far from the origin, so distance of at least 1, the function will output negative I. So this picture is trying to show you how that function behaves. This sort of light pink circle, these are the complex numbers whose output is I under this function. And purple are the complex numbers whose output is negative I. As we discussed in the previous video, I can't actually show you a picture, like a graph of this function, because complex valued functions graphs live in 4 dimensions. But there are ways of getting around that, and sometimes you can do like heat map kind of things to see what the function is doing. And so this is a 2-dimensional image here, but it's representing what's happening in 4 dimensions with this function. This is not a literal graph, but it gives you some idea of how the function is behaving. So now I claim that if you take the limit as z approaches I of this f, that limit won't exist. The reason is because if we approach I from the north, well, if you come in from the north, the function values are all negative I because you're all in the purple. So if you take a path from the north, you're just outputting negative I, negative I, negative I, so the limit of f of z appears to be negative I. But if you approach I from the south, coming up this way, the function is outputting I the whole time, I. So as you come in from the south, you're trying to limit to I instead of negative I. And so what's happening is at the boundary of this circle, there's a tear in the function. There's a jump, if you like. There's a jump from I to negative I. It's like a jump discontinuity from Calc 1. But when you're inside the circle, it's fine. There's no tears. And when you're outside the circle, there's no tears. But along the boundary of the circle here, the graph is literally torn. It jumps from I to negative I. So the limit as z approaches I doesn't exist because you're simultaneously approaching I and negative I. The limit as z approaches 1 also won't exist for the same reason. If you try to approach any of these points along the boundary of the circle, you'll get a limit that doesn't exist, because if you take a path from inside the circle and compare it to an input path outside the circle, you're going to get different limits for your outputs. So here's an example of a function whose limit doesn't exist at a particular place. So here's just another example where you can formally show that some limit doesn't exist. And I should point out to you that, not that I expect you to remember, but we did essentially the same example in Calculus 3. So this is a very Calculus 3 flavored problem here. We have to show that as z approaches the origin, 0 plus 0i, this function here has no limit. And sorry, this period cut off my sentence too early. Show that this limit, blah, blah, doesn't exist is what it should say right here. Show this limit doesn't exist. Okay, so how would you do that? Well, if you go back to a complex plane like this, you have to explain why there are multiple different ways of getting to the origin that will get you different limit values. And so what I'm going to do is I'm going to approach the origin, or 0 plus 0i, along the positive real axis where y is 0. So in this picture here, imagine walking towards the origin like this, from right to left to the origin. Well, if y is 0, you plug in y equals 0 into this complex function here, you get the limit as all that's left is x. Limit as x goes to 0 of 0, basically, right? So the output is 0. So along the positive real axis, you're just outputting 0 the whole time. But if you approach along a 45-degree line where the real and imaginary parts are equal, so if I go back to my picture, you're approaching along this line here, right, where the real and imaginary parts are the same. So here, like at this point, the real and imaginary parts are 1. Here they're both 2. Here they're both 3. Well, if y equals x, then we can transform this limit into another one involving only x. So plug in an x for y, plug in an x for y, and now you're taking this limit. The limit as x goes to 0, x to the 4th I over 4x to the 4th. When the dust settles after you cancel out, you just get an I over 4. So depending on the path we take to the origin, to 0 plus 0i, the output limit is different. Therefore, the overall limit doesn't exist. This limit here doesn't exist. Your function is simultaneously trying to limit to 0 and also I over 4 and maybe other things, who knows. But as soon as you get to disagreement like this, just like in Calculus 3, you say, no, the limit doesn't exist. This is the idea of a complex limit. So you're sort of input pathing inside the complex plane towards a number and then asking what do the outputs do? And sometimes the outputs go to different places, so the limit doesn't exist. Here's an example with this one, and here's an example with this function here. So quickly to wrap up, once you have the notion of a limit, you can very quickly get the notion of continuity. And this is the exact same definition from Calc 1, but with complex numbers now. A complex valued function is continuous at a particular complex number, if and only if this limit exists right here. So as z gets close to a plus bi, and apologies, there should be an f of z right here. Apologies for that missing. The limit of f of z as z approaches a plus bi is f of a plus bi. And so what you're doing is you're forcing the function to have no tears or no holes in it by asserting this limit thing. So as inputs get close to a plus bi, outputs go to they get close to the output they're supposed to get close to. That's all this is saying. With, again, my apologies, there should be an f of z right here in this empty space. Something didn't compile properly or something. Okay, anyway, and then a function is continuous just in general if it's continuous at all points in its domain. And pretty much anything you write down that's not piecewise will be continuous. That was true in Calculus 1. In Calculus 1, if you just write down like x squared plus cos x or whatever, you're going to end up with a function that's continuous. Same thing with complex functions. You have to kind of try to write something down that's not continuous for a domain point, for a point in its domain. Something piecewise is the easiest way to do it, like this. This function is not continuous along the boundary of this pink circle, but I had to do something piecewise to get that kind of wackiness to show up. Okay, so at the end of this video, you should mainly just be comfortable with the idea of a complex limit as defined like this, and know that continuity is defined in terms of limits, just like in Calculus 1. Where we are going next is defining complex derivatives. Those are limits. Complex functions are differentiable complex functions are continuous, but we'll stop this video here.